So one of the questions you might be having is that if we can do a um, electrophilic addition, say that's at HBr, and follow Markovnikov's rule, is there a way to get the other one? What if we want the other product? Or we would say like an anti-Markovnikov's addition. Is there a way to get there? And I'm so glad that you were asking yourself that question because there is a way. We're going to use HBr, but we're going to change the conditions slightly. We're going to add a compound that comes from a family known as peroxides. Peroxide is that oxygen that's singly bonded to another oxygen. Probably, remember something like hydrogen peroxide from general chemistry. And the R in this case can be hydrogen or carbons. But throwing those peroxides in completely changes the mechanism of the reaction. Because what happens is instead of going through a carbocation mechanism, when peroxides are present, it goes through a radical mechanism. So adding peroxides causes this to be a radical reaction. All right, so let's look at the mechanism for this. Because it's radical, we're going to look at initiation, propagation, and termination. So in the initiation step, that oxygen single bond is very weak and easy to homolytically cleave. And we get two radicals from a non-radical. Now, in the first propagation step, one of those OR radicals will react with HBr to get a bromine radical. And then we're going to take that bromine radical and react it with the alkene. So we'll use the pi electrons here to form that bond. Now I want you to notice a couple of big differences between this and the mechanism we talked about on the previous page. First of all, it involves a radical, so there's no carbocations. Secondly, go back up to your notes real quick. In a hydrohalogenation that goes to a carbocation, what atom got added first? Let's go back up and look. In this mechanism, the hydrogen got added first. In this radical mechanism, the Br adds first. Yeah, normally in the past we've done these radical mechanisms where there's two propagation steps. We're going to do one more just to kind of show the propagation step that gets us to our product. So we're going to take this radical from the previous step and react it with HBr. And so now you'll see that the hydrogen here adds second. And then finally with the termination step, just pick two radicals and put them together. Now, why does this go through a radical? Well, we know why it goes through the radical mechanism, but why does the bromine end up on the less substituted carbon? So an anti-Markovnikov's addition. And it has to deal with the fact that we're getting the more stable radical when the bromine adds first to the less substituted carbon. So let's talk about how we can utilize this in terms of synthesis, because we're gonna talk about more multi-step synthesis at the end of this unit. So how do we use these kinds of reactions to our advantage? So let's say we have this alkene, and our target is this. Okay, well, we know we added an H and a Br. Question is, how did we add it? Well, the hydrogen went here, and the bromine went there. Hydrogen went to the less substituted carbon, bromine went to the more substituted carbon. Well, that's a Markovnikov's addition. So I can do that simply by just adding HBr and nothing else. Maybe I keep the temperature cold, but I'm not going to add peroxides. Because if I want the opposite regiochemistry, again, I did the same thing. I added H and Br, but the H went to this carbon, the bromine went to the other carbon, the less substituted carbon. That's an anti-Markovnikov's addition. In order to do that, I'm still going to use HBr, but I need to add peroxides in order to influence or change the mechanism. To go from Markovnikov's to anti-Markovnikov's, I have to use the peroxides. So this is, again, an important tactic that we'll utilize when we start talking about multi-step synthesis and combining a lot of the reactions we've highlighted now in the past couple of units.